15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Da-da-da-da! That was a fanfare, by the way, to celebrate episode 150 of the Space Nuts podcast. Hello, I'm Andrew Dunkley, your host, and with me, as always, is Professor Fred Watson. Hi, Fred.
Hi, Andrew. I can't believe we've got to 150.
I think we lost count somewhere. We started it like that. It's like that thing the kids used to play tricks on me. That, Dad, I can count to 100. 1, 2, miss a few, 99, 100. That's where I think we went. This is really only episode 4.
Yeah, well, it feels like episode 1026.
It does, doesn't it? Yeah, it feels like we've been doing this forever. Well, it's probably over 3 years now, I guess, or it'd be getting on 3 years. And
that's right.
You add all our radio programs to it, and it's getting on.
It is in the thousands.
23 years.
Yeah, that's right.
And if you were to add all the other radio shows you've done over the years, Fred, I dare say you've probably had more airtime than me.
It's not impossible.
Now, we dedicated this show to answering questions, and we got a whole raft of new questions since our last episode when we put out the appeal, and some people have come up with some awesome thoughts, things that they've really wanted to know. And we're going to cover everything from water in the universe to Planet 9 to Hawking radiation to the afterlife. It's all been asked about, and we will do our best to answer your questions today on our 150th edition of Space Nuts. So let's start, Fred, and we'll go with a question from Paul Batty. Hi, Paul. Thanks for your question. He says, hi, Andrew and Professor Fred. Really love the show. I listen on Radio Australia. I didn't even know we were on Radio Australia. There you have it. Anyway, question. How rare are liquids in our universe? They're quite common on Earth, but I suspect that this state of matter may be rare. There's two parts to his question. Second part is, if I may, given wherever there is liquid water, you will find life. I'll put a pin in that for the moment. Perhaps wherever there is liquid water anywhere else in the galaxy, we could find life. Though I suspect, going back to the first question, that liquids sustained over billions of years is very rare. Is this correct? Thanks again for the show. Where do we start on this one? We have talked about liquid water in the past, and I suspect he's spot on in terms of liquid water in the universe. It does appear to be a rare thing.
Yes and no, Andrew.
Good answer.
And, well, let's get to the point. In terms of water generally, and by that I mean the molecule H2O, no matter what form it's in, that is the most common two-element molecule in the whole universe. So the raw material of liquid water is everywhere, but a lot of it is in a vapor form in what are called molecular clouds. It's basically part of a nebula, a gaseous nebula. So it's only when you get it on planets that there's a possibility of it becoming liquid. And the normal situation, and certainly this is the situation on Earth, if you have a planet which is within the Goldilocks zone of its parent star, so it's at the temperature that liquid water can exist, but also has an atmosphere which effectively stabilizes the body of liquid. So if you have you put a planet in the Goldilocks zone, cover it with water, if you've got no atmosphere, it simply evaporates and becomes water vapor, gaseous water in space. So you need this blanket of, in our case, air to maintain the liquidity. And that situation could be fairly rare. We don't know, but it could be a rarity. However, liquid water can occur in other ways, and we know of several examples in the solar system. It's about half a dozen, including the planet Mars, where there is liquid water underneath a layer of ice. So instead of an atmosphere keeping it liquid and in equilibrium, the ice is protecting it from the vacuum of space, and the liquid water is sustained underneath the ice. So you've only to think of Europa, Ganymede, Enceladus, Titan. all these moons of Jupiter and Saturn, plus, as I said, Mars, because last year there was a discovery made of a large reservoir of water underneath the southern polar ice cap.
Yes, that's right. I remember.
So it's rare, but perhaps where there are planets, it's not so rare, and that's really why we're so keen on evaluating all these exoplanets, planets around other stars that are being discovered. Second question. If I may, he says, given wherever there's liquid water, you'll find life. Perhaps
on Earth, I think he means, yes, which would be right.
On Earth, that's right. But that, of course, is why we're so excited about these places where we know liquid water exists. For example, Enceladus. Saturn's moon Enceladus has an ocean underneath the icy surface, which we know from Cassini's results has hydrothermal vents at the bottom of it. So there's heat processes taking place there. That's the kind of environment in which life kicked off on Earth. Maybe, just maybe, life has kicked off in the oceans of Enceladus also. But at the moment, we've got no way of finding out. Enceladus actually offers the best possibility of finding life in such an environment, though, because it's squirting out this water in these jets from its southern polar region. Cracks in the ice let the water leak out. It's got fountains of tiny ice crystals, which have already been sampled by Cassini, but there are at least 3 missions being planned to have a closer look at these with a view not just to looking at the kind of chemical makeup of it, but the biochemical makeup, these perhaps prebiotic chemicals, lipids and proteins and things of that sort. So it's a great question, and yes, we're onto it.
There you go, Paul. So yes, there is liquid water in our solar system, and there's certainly, and that sort of opens the door to the possibility that this is not an uncommon thing in other systems outside of our own. So, is there life in that water? That remains to be seen. Of course, the other side to this coin, Fred, is that it's also possible that life has adapted to liquids other than water, like methane.
Yeah, exactly. So, and that, of course, you're thinking of Titan, Saturn's largest moon, Titan, which does have liquids on its surface. There's liquid ethane and methane, and it is just possible that there may be life forms that have developed in that using ethane and methane as their working fluid. Another really interesting question. We need to send a spacecraft there as well to find out.
Yeah, I think we're running out of spacecraft. But there's so many places to explore. And the wonderful thing is we've got the technology now. We can do this. It's not cheap and it's not fast, but it can be done and has been done more often now than ever before, really. So thank you, Paul, for your question. Hopefully you got the right answer. And we will move on to a question from Jake Bain. He's responding to a post we put on our Facebook page the other day about that house-sized asteroid that basically passed Earth the other day. I think it passed sort of half the distance to the moon, if I recall correctly what the story was about. Anyway, Jake says, so curious, what would have happened if it hit a city, or would it have been another fireball like the one that was over Russia, Chelyabinsk's talking about? Size of a house, what sort of damage would that do?
Yeah, that's on the... It is on the scale where there would be damage on the surface. So the Chelyabinsk meteorite, or superbolide to give it its proper name, back in 2013 was about that size, about 15, 20 meters. That hit the atmosphere at 30 kilometers per second, got down to a height of 30 kilometers above the surface before it exploded. And of course, it was the shockwave from that explosion that did the damage. It smashed windows and knocked down walls and things of that sort. So you've basically got exactly an example of what Jake's question is. The Chelyabinsk incident was pretty well what would have happened if this house-sized object had hit the Earth's atmosphere, excuse me, months or so ago, whenever it was. There's one caveat with that, though, and that is that asteroids, or small asteroids, large meteors, whatever you want to call them, they vary a lot in composition. Some of them are made of almost solid iron, and an iron meteorite of that size coming through the atmosphere would not, almost certainly would not explode in the atmosphere and disintegrate. You get a big chunk landing on the ground. So there would be an impact site with possibly a crater. And if that if that impact site was the middle of a city, it almost certainly would have done catastrophic damage. It would have, been a major civil defense problem. So the one that missed us, well, a miss is as good as a mile. The good news about these things, as I always say, excuse me, Andrew, I'm losing my voice here. The good thing about them is that these things have been whizzing by the Earth for billions of years, and it's only now that we know about it because we've got the wherewithal to measure them. So there's really, the situation has not changed much over time, but we now know much more about the Earth's environment than we did. And so we recognize the risks. It means that we are also working on schemes to try and deflect one of these if it turned out that over a long period of time we could see that it was going to collide with the Earth. At the moment, there's nothing on the horizon for a collision for at least the next 100 years. So
that we're doing
of. That we know of. Yeah. That's why I said there's nothing on the horizon.
There's always the great unknown.
There is, yeah.
It always takes me back to that great science fiction novel by Isaac Asimov called Nemesis, which was about an impending collision with Earth, an end of days kind of an event, and they overcame the problem by sending an orbiting spacecraft to deflect it slowly, veer it off course over a number of years. Which would work, I guess.
That's what would happen. That's right. It's all about how much notice you've got. If you've got 10 hours, then you're talking about civil defence measures. Yeah. But if you've got 10 years, then you can do something about it. That's right.
Okay, Jake, thanks for the thoughts and thanks for visiting our Facebook page. Now, let's move on to a question about Planet 9 from Simon Adam in Melbourne. He says, and thank you, Simon, if we are so good at using Newtonian mechanics to predict when a solar eclipse will occur in 200 years from now and when Jupiter will rise and set to the second and the like, why can we not use this method to find Planet 9? I appreciate Planet 9 is a long way away and very dark, hence it's not straightforward. But if you assess Neptune to move over here and Uranus to move over there, why can you not plug these abnormalities, along with other known orbital anomalies, into a smart algorithm which shows that a body of this size must be over this location? I'm sure the technique is being used, but why isn't it a sure thing?
Great question. And so Simon's absolutely right. This technique is being used. That's exactly why we think there is a Planet 9 out there. And of course, this what Simon said is exactly how the planet Neptune was discovered.
Simon said, that's a good one, Fred. Sorry.
Yeah. It was because of anomalies in the orbit of Uranus that didn't make sense. That was the prediction that led to the discovery of Neptune. In fact, the mathematics were so good, and this is back in 1846, that when they finally got around to looking for Neptune, where the mathematicians said it should be, they found it within an hour. It's an hour of observing. So the method works. The reason why, in this case, it isn't a sure thing is that we're dealing with vastly greater distances than what we have in, what you might call the inner solar system out to the orbit of Neptune, because these objects are tens of times further away. And the only things that we've got out there whose orbits might be modified by the presence of a Planet 9 are these extreme, what are called extreme trans-Neptunian objects. They're things in the Kuiper belt, way out there beyond the orbit of Neptune, and they're tiny. They're little asteroids, not planet-sized things, which move in response to another planet. These asteroids do move in response to a planet, but each one of them represents a very small quantity of mass. So what you've got to do is lump them together and look at the way they behave as a group, and it's that has led to the conclusion that there is a Planet 9, because their orbits all align. It's a selection of, I can't remember how many it is, it's about half a dozen or a dozen or something of them that have very peculiar orbits in terms of their their alignment and the inclination, the tilt of the orbit. And it's those factors that get fed into exactly the kind of algorithms that Simon's talking about that reveal that there is something out there modifying this part of the solar system. But it's not big enough and not close enough to have an imprint on the orbits of Uranus and Neptune, and for that matter, Jupiter and Saturn, the planets of the outer solar system. So you're on the money, Simon, with what you're suggesting, but it's just the sheer distances involved that make this such a difficult project.
Okay. We will find it one day, I'm sure.
I think we will too. Yeah, I think so. Remember where you heard it first.
Yes, indeed. Thank you, Simon. Great question. We love talking about Planet 9, only because we all know it's there and we're just waiting for someone to spot it. But, when we talk about distances, Fred, we sort of limit our thinking to the likes of Neptune and Pluto and the other Kuiper Belt objects. But we're talking about distances far beyond that, which becomes incomprehensible to a certain degree.
Yeah, but much greater distances. I don't have the numbers to hand. I was writing about them quite recently, but I don't have them to hand. But you're talking many tens of times further away than Neptune is.
Yeah, that's just hard to contemplate. But anyway, thank you again, Simon, for your question. And Simon says we need to take a break. You are listening to episode 150 of Space Nuts with me, Andrew Dunkley, and Fred Watson.
3, 2, 1.
Space Nuts.
Now, Fred, we are going to look at a question from Judas Falling. I just love your name, Judas. Judas Falling. It sounds like the name of a great science fiction novel or a movie. It's just terrific. Anyway, he says he's a long time first time. So he's been listening for a while. First time he's contacted us to ask a question. Anyway, he says, I'm always confused when we talk about the universe being flat. Does this mean the expanding universe is not like a spherical bubble, but more like a plane, like the galactic plane, or the way our solar system has a roughly flat plane? That is a great question.
Absolutely is. And I think it is an indictment on we astrophysicists, because we use this term, and if you talk about a flat universe, then naturally people are going to imagine something like the solar system or the galaxy, which is flat. It's basically concentrated in a plane. But that's not what we're referring to when we talk about the universe being flat. We're referring to the underlying geometry of the universe. And this is where it gets a bit of a headache. So the way to think of this is, instead of, well, let me step back. Judas's question starts, does this mean the expanding universe is not like a spherical bubble? No, it doesn't. So the expanding universe, as far as we know, is like a spherical bubble. So keep that picture firmly in your mind. It's expanding, as far as we can tell, it's expanding the same in all directions, which means, it's basically got spherical structure. So it's a bubble. It is not a flat disk or something like that. It is actually a bubble. Now think of it squashed to 2 dimensions. I know I've just said it's a bubble. So what I want you to do now is imagine you've taken away one of the dimensions. So what you do have is a flat surface. That represents the universe pretty well, because the geometry of a flat surface is the same, it's what we regard as standard. For example, Pythagoras' theorem works, and the angles of a triangle all add up to 180 degrees. That's true on a flat surface. But if instead of that, our universe compressed into 2 dimensions was curved like a sphere, for example, then you would have a different geometry. You wouldn't have a right angle triangle making Pythagoras' theorem work. You wouldn't have triangle angles adding up to 180 degrees. They'd become something quite different. So that is one sense in which a universe could be curved. There is another sense as well, which is quite interesting. The universe could be saddle-shaped. And what we mean by that is if it's curved one way in one direction and the other way in the other direction. You might think of a saddle, it goes on the back of the horse, so it's curved around the side of the horse, but the front and back of it are curved upwards, so you don't fall backwards and forwards. That's exactly the kind of geometry. It's in mathematics called a saddle.
It's also the shape of a putting green that golfers hate the most.
Absolutely, yeah, because you don't know where the ball's going to go. So that's another possible geometry of the universe. If you imagine your universe collapsed into two dimensions, but it forms a saddle, then it's got a curvature. It's got this curved geometry, and the bottom line is that all our measurements, our experiments, and everything points to the fact that the universe is actually flat, and that means its geometry is like a flat plane, the geometry of a flat plane. So that's what we mean by it. It's a very poor descriptor, because it immediately conjures up exactly what Judas has said, a compressed, a disk-like universe. That's not what it means.
Okay, so it's a sphere spreading out in all directions at the same time, but it's flat.
Yeah. Its geometry's flat.
I'm confused. I'm always confused. But
this is the one place where Space Nuts lets us down, because we can't put diagrams in.
No, well, we
should get somebody to put one on the Facebook page or something like that, showing a saddle and a curved space.
Yeah. Anyway, Judas, you asked the question, and that was the answer.
But the main thing to remember is the universe is like a spherical bubble, not like a tabletop.
It's not a disc. It's not a flat plane kind of
even
thing.
Though it's flat.
Yeah, even though all right. Moving on. Thanks, Judas. Moving on. This is a question from an astrophysicist observer named Andrew Mortimer. Hi, Andrew. Thank you for your question. He says, hi, Andrew and Fred. Thank you for your show. It's a great time to be talking about all things astrophysics with all the great new observations. A quick question. Can we observe Hawking radiation in the recent black hole image? Personally, I hope so. Can we?
I think the short answer is no. And that's because Hawking radiation is incredibly weak and has never actually been observed. We know it exists as a theoretical entity. It's accepted as reality. It means that over very, very long periods of time, black holes evaporate. But it's so low. I think you could probably say it's so low as to be unobservable. I might be wrong with that, but I do not believe any kind of Hawking radiation has ever been observed. What has been observed are analogues. You can set up an analog of a black hole with radiation. In fact, you can do it with sound waves. It sounds bizarre, but you can do that. And I think Hawking radiation reveals itself under those circumstances. But in direct observations from a black hole, no, it's not been done yet. Even with that supermassive, 6.6 billion solar mass black hole at the center of M87, even there we can't see it.
It sort of brings up the point that there are a lot of things we know about that we have not seen. And up until the other day, we had never seen a black hole. We haven't seen Hawking radiation. We haven't seen dark matter or dark energy. But we know they all exist.
Yeah, that's right. Yeah.
It's one of the strange anomalies of astrophysics, I suppose, and probably one of the key frustrations of the role, I would imagine.
Yeah, it is a bit annoying. That's right. When people think you're just making it up as you go along.
No, never. No. Although sometimes that's how discoveries are made. You've got to come up with a theory. And you work around the theory until you prove it wrong or right.
Exactly.
That's science, isn't it?
It is the way science works. That's true.
Okay, Andrew, thank you so much for your question. Hope we covered it. It was brief, but sometimes the answers are that simple. No, can't say it. You're listening to the 150th episode of the Space Nuts podcast.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Finally, Fred, let's tackle a couple of questions, shall we? Wait a minute.
That's a great idea.
That's a good idea. This is episode 150 of the Space Nuts podcast, where we asked you to basically send in some questions that have been sort of teasing with your brain a bit of late. And the next question comes from Richard Adams, and it sort of harks back to Judas Falling's question about the shape of the universe. He's asking about the shape of black holes. Firstly, I've been listening for quite a while now and thoroughly enjoy your podcast. My question is about black holes, or more precisely, the direction and shape of black holes. It just seems strange to me that something of that magnitude is simply a one-dimensional well, drain hole in space. They exist in a multi-dimensional fabric, so shouldn't they also be multi-dimensional? For example, a very large black billiard ball shape rather than the rim of a black frisbee disc. I guess this might quash the theory that they may lead somewhere, but hey, I'm just saying the disc shape doesn't make sense to me. All the best. Good question. What is the shape of a black hole? Now that we've taken a photo of one, are they able to glean? That's right. Are they able to glean the shape?
Yeah. Well, yes. So let's just clarify a couple of things here. The black hole itself is not one-dimensional. It is zero-dimensional. It has 0 dimensions. It's just a point in space. Even though the space around it is multidimensional, of course, the black hole has no length. Basically, it's a 0 dimension. And that's why the physics of them are just so hard to try and understand. In fact, most of our known physics breaks down in a situation like that, because you get things like an infinite density, which is how you define a black hole. It's a point in space where density is infinite. But there is a shape to it. And in fact, there are two things here that you can attribute shape to. The first is the event horizon, and that's the most important feature of the black hole, and that's what we saw in the image, the shadow of an event horizon. So that's the point of no return. It's the point beyond which even light cannot penetrate. So if you were looking at a black hole, sort of, a naked black hole, you might call it, that what you would see would be the event horizon. And the diameter of that event horizon sphere is dependent on the mass of the black hole. So for a black hole of the mass of the Earth, the event horizon is 18 millimeters in diameter. It's the size of a golf ball, pretty well. That's the size of the event horizon.
No, really?
Yeah, it's tiny. For a one solar mass black hole, a black hole the mass of the sun, its event horizon is 6 kilometers in diameter, but it's still pretty small. Yeah, they're weird things. Now, what I was going to say, though, is that, and I'm harking back to distant memories here, but I think I'm correct in saying all this. The physical parameters of the black hole include things like its electrical charge, whether it's rotating, something we call angular momentum, and they can change the shape of the event horizon. I've got vague memories of looking at diagrams in physics books showing pumpkin-shaped black holes because they're rotating. I might have the exact details wrong, and I should check them up. But that's the bottom line: is the event horizon is not always a perfect sphere. It can be
not a Jap pumpkin, as we call them in Australia. Otherwise known as a squash.
A squash, yeah. Yeah, that's right. No, it's not that shape. It's just like, I'm not quite sure what a good analogy would be.
A traditional Halloween pumpkin.
That's exactly right. A traditional Halloween pumpkin. Thank you very much for that, helping me out. We didn't have pumpkins where I grew up, Andrew. I'd never seen one until I came to Australia.
Really?
Yeah, absolutely. Yeah.
That's very interesting.
Yeah, I used to read books about Halloween and think, what on earth are they talking about? Anyway, never mind. That's a different story. So you can get different shaped event horizons. But the bit that's like a disc, and maybe this is what Richard's thinking of with the Frisbee shape, that's the accretion disk. This is the swirling disk of material that is circulating at very high velocity around the black hole event horizon before it crosses over that and disappears into the black hole never to return. So it's there is a disk to it, but it's the the stuff we can understand. Actually, this is the gas and probably bits of stellar debris being sucked into the black hole that swirl around like the water going down the plug hole, that kind of feel to it, but at very high energies. Even though, their temperatures are in billions of degrees, that stuff that's whizzing around the black hole. But we can understand the physics of that. It's at the point itself that physics breaks down, where you've got this zero-dimensional singularity. Very bizarre.
So it is not necessarily a sphere, but it ain't flat.
That's right. The black hole itself is not flat. Yeah.
Okay. There you go, Richard. Hopefully that leads to a better understanding of black holes. I mean, the astronomers and astrophysicists are still trying to understand black holes, but we're getting more and more information, and this photograph is being analysed very, very thoroughly, and very soon we hope to have another photo of a black hole, and be interesting to compare the two and see what the differences are. And maybe one will be shaped like a pumpkin and maybe one will be shaped like a potato. Actually, I'm thinking, Fred, I wish I grew up where you were from, because I hated pumpkin as a kid. I'm used to serve it every other night. And they used to force me to eat it. Now I love the stuff. It's just it's a matter of training your mind. That's what it's
Indeed,
about.
that's right. And your palate.
And your palate. Yeah, that too. Okay, thanks, Richard. We'll move on to our final question in the 150th episode of Space Nuts. This one comes from Ralph. We saved this to last, Ralph Haney in California, because it sort of takes us into a new realm. Dr. Fred Watson, a hypothetical question, if I may. Personal beliefs and experience as aside for just a moment, I beg you to consider one question to rule them all. If you were to learn when you die that there is in fact a higher being, a creator of our universe and existence, and you were granted one solitary question as a scientist and astronomer, what would that question be? Not the meaning of life, that's 42. Would it perhaps be regarding dark energy or pre-Big Bang or extraterrestrial life or something far deeper and mysterious than even space nuts have discussed? Dr. Watson, what would you ask? We need to know. What a great question. I love it. I love it.
Yeah, it is. It's a great question. And all the things that Ralph mentions, like extraterrestrial life, dark energy, and what things were like before the Big Bang. They are all questions that I'd love to ask, as any astronomer would do. But the one I think that would come to mind is, okay, why? What's it for? Mm-hmm. Why on earth have we got it? And what leads me to that is thinking that you and I, Andrew, have explored in the past on Space Nuts, the possibility that we may be the only species in the entire universe with the mental capacity to try and understand the universe and to perceive it and to study it and to know it's there. If we're the only species like that, and we manage somehow to wipe ourselves out, or an asteroid gets us in the end, or whatever it is, what on earth is it all for? Why is the universe there? It just doesn't make any sense at all. And I think that's a point where our reason breaks down. It was Pauli, the great physicist Pauli, who postulated, he made the comment that, maybe at the most fundamental level, we cannot understand what's happening in the universe because we are part of the problem. We're in it. We're part of it ourselves. And so maybe we are conditioned to think in a way that really doesn't allow us to perceive the great truths. And he was thinking about things like the nature of time and, the nature of the Big Bang and things of that sort. But I think it goes to the heart, to the wider question of why is the universe there? We're part of it. And so it's not really an issue that can be addressed.
And being on the inside, as you said, may be the most limiting factor of our analysis of the universe. If you were able to step outside it and look upon it, maybe you'd go, you'd
wow. Get it. Oh, that's what it's
right. That makes sense. Yeah. Those black holes all do this, or something to that effect.
Exactly. But we're not, we're inside it. And that's a bit of a problem. But it's, to be honest, Andrew, being inside it is better than the alternative.
Yeah, I suppose
because that suggests a rather drastic change.
So your question would be to God.
Why is it so?
Why is it so?
Why is it there? You know, what's the universe for?
Yeah.
Is it just a bit of entertainment on the part of the creator? Who knows?
My question, if I may indulge myself, is
yes, sure.
How is their existence?
Yeah.
Because I got a friend, and often when we're playing very bad golf, we talk about these sorts of topics, and we talk about if you sit down quietly by yourself in the dark and just contemplate the fact that we exist, it is miraculous in itself. And, you know, how is it so? How do we exist? Where did it all come from? And, you know, that leads to the why and
yes,
so
it does.
many more questions.
You've got things like the nature of consciousness and all this sort of thing that comes.
Yeah, and the question of a soul, and the question of as Ralph suggested, a deity that sort of is all being and all knowing and a creator. But okay, if that's the case, how did they come into being? Why do they exist?
Well, the
questions are ongoing.
Ongoing, yeah.
But it's a great question, Ralph, and we do appreciate it. And hopefully Fred's answer to your ultimate question was adequate. That's what we strive for here. I've said it before.
Excellence, forget it. We just do our
just to be adequate. Yes. Thank you to everybody who sent in questions. I think we got all the questions answered that came in post episode 149, except for one where they asked us to list our top 5 favourite science fiction novels. But as a science fiction not fan, that would have been not easy for you, Fred. But I could have, yeah, I'm sure I could have.
And of course,
I was going to say Parallax, but she preempted me and said, "Yes, I've read it. I really enjoyed it, and I can't wait for your next one." So,
there you go. That's all you need to know, Andrew. That's all you need to know.
and the shameless plug I managed to get in again for the book. Any word on yours, Fred? Is the publisher got?
Well, yes, its name has changed again.
Oh, what's it going to be called now?
Cosmic Chronicles.
Oh, I like that.
Yes, I do too. Yeah. And so I've just got the publisher's notes to the editor as to what's going to happen. They're taking out all my jokes, which I'm not surprised about because most of them were rubbish anyway. But it'll be fine. It'll be fine. It might have, though, and this is something that I'm rather chuffed about, Andrew. When I'm going back 50-odd years now. When I was still at school, I used to have a rather artistic flair, and I did a lot of sketching and drawing, which earned praise from various people. And we're thinking of trying to get some diagrams in, which I'm going to draw not with a computer but with a pencil.
Oh, maybe you should draw one of the spherical flat universe.
That's right. That's
for Judas, and we can get that on the cover of our next Facebook post.
Yeah, you never know. I might do that. The flat universe. All right. So we'll see how it goes.
Yes, indeed. I'm looking forward to it. And another thing that people might not know about you, Fred, is you like to compose and play music.
Yeah, that's right.
There's been a few over the years.
Indeed, that's right.
Yeah. We're going to have to get you to play the guitar on the podcast one day.
Yeah, I should do that one day. Yeah.
That'd be fun. I got mine over here.
Good on you.
Yeah. All right, we better call it quits on episode 150, but we will be back with episode 151. Thanks to everyone who contributed. I know we've got a little bit of a backhaul of questions that we will get to, so never fear if you missed out this week. Fred, it's been fun as always. Thank you for 150 terrific episodes.
Thank you too, Andrew, for putting up with it. We'll speak again very soon.
We will indeed. Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thank you so much. Look forward to catching you next time on Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.